All right. This is just a quick walkthrough of the 6.6 notes for my absent and quarantined students. So we have several rules we've talked about so far. This section just sort of puts everything together. There's this idea of a complement rule. Okay, so and remember, a complement is everything that's not the event you're looking for. And so we know that the probability of a complement is 1 minus the probability of the event itself. Okay, so we've got that. That rule right there. So one of the ideas, there's a couple of special complements that make it easier for us to do problems. The first one is the idea of at least one. At least one. And so the probability of getting at least one is 1 minus none. So if I'm talking about like 5 different things and I say, oh, what's the probability that I roll a die 5 times and I get at least 1 even? Okay, so the only thing that wouldn't give you at least 1 even would be no evens. Okay, which is usually easier to count than it is to do the first one. So at least 1, that complement there is 1 minus none. And we use that quite a few times, okay? The other idea is this neither A nor B. It's neither one. It's not A and it's not B. And if you think in terms of a Venn diagram, where you would be is on the outside of all of those circles. So the complement of that would be A or B. Remember, A or B is anything that's an A, anything that's a B, and anything that happens to be both. Okay, so neither A nor B would be everything except for that or. So if you know how much is in the or, then neither one of those things would be on the outside of that. Keep in mind that on your formula sheet, you've got the rule for addition of probabilities, or in other words, to find that or, which you might need. So the probability of A or B is the probability of A plus the probability of B minus the probability of that overlap that you don't want to count twice. Okay. Also, we talked about multiplication. For dependent events, you want to be careful because if I want to know the probability of A and B happening, I would take the probability of A times the probability of B given A. But if they're independent, the probability of B and the probability of B given A, those would be the same thing because independence doesn't change that probability. And so you can just multiply straight. Okay, but you got to be careful. When we're talking about independence and we want to do tests for independence, we want to start off and say, okay, if probability of A is equal to probability of B, then they're independent. Actually find the two and make your conclusion. Whereas mutually exclusive or disjoint, the probability of A and B equals 0, then you've got those disjoint. That overlap is there. Okay, so these are kind of the things you need to have memorized, the things you kind of know. Not mentioned on here is that conditional probability formula, which is also on your formula sheet. Okay, so I've already got these problems worked out, so just bear with me here, but I just want to talk you through. So suppose your teacher is trying to demonstrate a probability concept and she is running out of ideas. Not a big stretch. She creates 3 bags and fills them with 20 Scrabble tiles. All right, so I'm going to move my picture over here a little bit. First question is, you draw 3 tiles out of the first bag, one after the other, excuse me, without replacement. All right, so the first bag, I'm going to draw 3 tiles out of here without replacement, and I want to know what's the probability of 3 vowels. Now, this is definitely going to be dependent because I'm taking them out of the bag without replacement. So the first time there's 20, and then the next time there'll be 19, and the next time there'll be 18. So the probability of getting a vowel is actually changing each of these times. That is what dependence looks like. Okay, so that would be 12 out of 20 times 11 out of 19 times 10 out of 18. Remember, your vowels are A, E, I, O, and U. That's where those are coming from. Okay, so I end up with that probability. What if I want to get 3 vowels, but I'm drawing 1 tile out of each bag? Now, in that case, there are 13 vowels in this second bag, and there are 6 down in the third. Okay, and so when I'm talking about these probabilities, this is going to be independent because whether or not I get a vowel in the first bag shouldn't affect the probability in the second bag. So the probability is, notice I've got 20 and 20 and 20 here. So the probability in the first is 12 and out of 20, and then the third there are 13 out of 20, and sorry, in the second there are 13 out of 20, and in the third there are 6 out of 20. So 12 out of 20 times 13 out of 20 times 6 out of 20, that's going to be 69%. Okay, you draw 3 tiles out of the second bag, one after the other without replacement. So again, we've got without replacement. So each time we draw, we're going to have 1 less tile there. And it says, what's the probability of not drawing an E, not getting an E? All right, so there are 9 E's and 11 not E's. Okay, so there are 11 ways to not get an E the first time, 10 ways the second time, and 9 ways the third time, giving us a probability of 0.145. Okay, so follow-up question then. You draw 3 tiles out of the second bag, one after the other without replacement. What's the probability of getting at least 1 E? At least 1 E. All right, so in this case, the only way I'm not going to get at least one E is if I get none at all. And I've already calculated that probability. The chance of getting no E's at all is 0.145. So every other situation has at least one E. Okay. Now you want to be careful because trying to calculate the probability of drawing 3 tiles and getting at least one E can be a little difficult because it could be the first E, or it could be the second E, or it could be the third E, or it could be these two, or those two, or all three. Except there's a lot of different ways to calculate at least one E. Okay, but there's only one way to do no E at all, which is why this is easier. All right, so we end up with 0.8551 minus that not going to happen probability. All right, you are going to spin the spinner at the right. The spinner has 2 blue regions, 3 red regions, and 1 each of yellow, orange, and green. Okay, and so what's the probability of the spinner landing on blue? So we could look at that and we could see that's a nice simple probability there. That's 2 out of 8. What's the probability of it landing on any color that's not blue? So what's the not blue? That'd be 1 minus that 25% or 75%. So those are complements of each other, blue and not blue. Now, we're going to decide to spin the spinner 4 times. This would be independent because I'm assuming that if we spin the spinner and we get blue, that doesn't change the probability of getting blue the second time. So each spin is going to be independent. And it says, what's the probability of getting blue each time? So if getting blue once is 25%, then getting blue each time would be 25% times 25% times 25%, or 0.25 to the fourth. That's going to be your 0.004. What's the probability of not getting blue until your 4th spin? All right, so it's easy to think, what would this look like then? If I don't get blue until the 4th spin, it's going to look like not blue, not blue, not blue, blue. And those are probabilities I can find. 0.75 times 0.75 times 0.75, that's my not blue, not blue, not blue. And then blue, 25%. Okay, so that'd be 0.75 to the 3rd times 0.25. In your calculator, you should end up with about 10% there. Okay, so I'm just following what's going to happen. Then it says, what's the probability of getting at least 1 blue? Now, if you're going to spin the spinner 4 times to get at least 1 blue, you need to be careful because it could be the first one is blue, or it could be the second one is blue, or it could be the third one is blue, or it could be the 4th one is blue like we got on number 4. Okay, so there's 4 different ways you could get 1 blue you'd have to calculate. And then you've got 2. So it could be the first 2 or the second 2 or the third 2 or maybe the first one and the third one or the second one. So all kinds of ways you could get 2 blue and then 3 blue and then 4 blue. There's all kinds of ways to do this. So the only way you're not going to get at least 1 blue is if you get no blue at all. Okay, now I can figure out the probability of getting no blue at all. No blue at all would look like 0.75 times 0.75 times 0.75 times 0.75. That's the only way you're going to get not blue at all. Okay, that's really easy. Not blue, not blue, not blue, not blue. Okay, it's a very easy calculation. End up to be about 0.316. So if the only way you don't get any blue at all, the only way you don't get at least 1 blue is to get no blue at all, that's 31%-ish. Okay, so the probability of getting at least 1 blue would be 1 minus that. So we're looking at about 0.684. Okay, so again, when we're talking about at least 1, okay, the only thing that's not going to give you at least 1 out of these 4 spins being blue is no blue at all. No blue at all is easy to calculate. So this is where the complement can really help us out. Okay, the next one says, what's the probability of getting at least 1 red? At least 1 red. So similarly, the chance of getting at least 1 red, would be like the first one could be red, or the second one could be red, or the first one and the second one could be red. Lots of options. The only way you're not going to get at least 1 red is if you get no red at all. So there are 3 reds on the spinner. So the probability of getting no red would be 5 out of 8, not red, 5 out of 8, 5 out of 8, 5 out of 8, which is about 15%. So the chance of getting at least 1 red would be everything else. The only way you're not going to get at least 1 red, okay, is if you get no reds at all. Okay, and so in that case, we would take 1 minus that probability to get our answer of 0.847. Okay, the next one, what's the probability of getting not all blues? So the probability of getting not all blues would be the complement of getting all blues. The only way you're not going to get not all blues is if you get all blues. And we've already calculated that up in question number 3. Okay, so if you look at question number 3 there, brought up a little typing box. Can I make it go away? There we go. Is 0.004. Okay, so we already actually did that probability. So 1 minus that gives me that 0.996. Okay, that's a lot easier to find the complement than it is to find the thing that you're looking for. Okay, so just in general, anytime you see at least one, you want to think that's the same as 1 minus none. And the probability of none is usually pretty easy to compute, and it's pretty straightforward. The at least one has a lot of pieces that you have to put together that can be quite a challenge. Okay, all right, and one other example here, I have a table. Just a reminder when you're dealing with ors, okay, what's the probability of someone being in junior college or in the Big Ten? So junior college, 27%, Big Ten, 23%. There's no overlap there, so I'm just putting those together. That would be 50%. However, junior college or 15 years, okay, 15 years is all 35% there. Junior college is that 25% there, and they are crossing at that 13%, which means we're including the 13% and the 27%. We're also including the 13% and the 35%. So remember, our formula says the probability of A or B, like junior college or 15 years, is the probability of A, 27%, plus the probability of B, 35%, minus the probability of where they cross, that intersection, which is 13%. So while junior college and the Big Ten are mutually exclusive, they're disjoint, the probability of A and B, they don't intersect, that's 0. Okay, on the other one, you have to be careful with that overlap. Okay, anytime you're trying to find an or, okay, or maybe you're missing something in this formula, don't forget about that handy dandy formula there. All right. If A and B are independent events and the probability of A is 60% and the probability of B is 40%, find the probability of A or B. All right, so find the probability of A or B is my instruction, and I know I have a formula for that. The probability of A or B is A plus B minus the and. Okay, and I know that I can put 60% in here because it was given, and I can put 40% in here as given. But in order to find the and, I have to go back to where it says independent. So remember, I know if they're independent, that it shouldn't change the conditional probability, but I don't see that as being an option with the things that we have. That I don't have the and there. Okay, so instead, I'm going to use that multiplication property. If they're independent, the probability of A and B should be A times B. And I know both of those. That gives me an overlap of 24%, which I can fill into that blank. So if this had said mutually exclusive, I could have put 0 in for there. But since it says they're independent, I know I can multiply. I can use that multiplication. If they are not independent, I would not be able to solve this problem. Okay, because the probability of A and B, this conditional probability, that would be B slash A, B given A, and I don't know that. I can't find that. If they're independent, I can do this multiplication. Otherwise, I'm out of luck. All right, just a reminder about turning our tree diagram into a table. Okay, in a certain city, 45% of the registered voters are Republicans, 40 are Democrats, and the rest are independent. Okay, so 45% and 40% give me 85%. That gives me another 15% for my independents. Also, 40% of the Republicans are women, 55% of the Democrats are women, and 60% of the independents are women. So we can find our women numbers from the table, and then, excuse me, those should add up to 100%. So the complement there would be the 60% men, the 45% men, and the 40% men. Okay, on our table, you'd want Republicans, Democrats, and independents. Don't forget that word total. And then men, women, and total. And again, to find each of the spots in there, you want to multiply down the tree. So to figure out Republicans that are women, you want to multiply down that branch of the tree. Okay, you're going to show that work and get that 18%. So again, you multiply down each branch of the tree to fill those in. And that allows us to see that 49% are women and 51% are men when we finally combine those probabilities together. Okay, so you should be able to answer questions such as, what is the probability you choose a person who's a woman and a Republican? That's just going to be that overlap, that 18%. And as long as you have shown your work in the table, there's no work to show. You've got it up there, you've got the product, etc. What's the probability you choose someone who's a woman? I can read that right off the table. That is 49%. What is the probability I choose someone who is male or independent? Male or independent. So I know that's going to be the probability that someone is male, which is 51%, plus the probability that someone is independent, which is 15%, minus those where they overlap, which is that 6% in the table where those two things overlap. Okay, so I'm using that or formula, all the A's plus all the B's minus both. Okay. And then what's the probability that a randomly chosen male is a Republican? So this is one of those given that's kind of hiding. What's the probability of a randomly chosen male? So we know the person is male. So that's like saying, what's the probability someone's a Republican given that I know they're male? So out of the 51% who are male, it looks like 27% of those are Republicans. And so my final answer, don't leave that decimal fraction, go ahead and divide that out, is about 52% there. Okay. Are being a woman and being a Democrat independent, justified? Now I'm gonna have to scroll down here. You're gonna lose track of my table for a minute. So if I was gonna make this argument, are they independent? I would start off and say, if they're independent, the probability of being a woman should equal the probability of being a woman given that you know she's a Democrat. Okay. So the conditional probability, woman should equal woman even if the person is a Democrat. Okay, so that's my argument. Those should be equal. So I look up at my table, and the probability of being a woman is 49%. And the probability of being a woman, given that I know the person is a Democrat. So I'm just looking at the Democrat part of the table, that 40%, 22% out of the 40%, that would be that conditional probability. All right, so that would give me 55% for that answer. Those are not equal. So they're not independent. If those were equal probabilities, we would know that we would have independence. Okay. All right. I have this little comic here, which you should read sometime when you have a minute. You can pause the video and read it. Okay. Just a reminder that a large percentage of a small percentage is still really small, and that a small percentage of a large number is usually still really large. Okay. All right, so I have an entomologist spots what might be a rare subspecies of beetles due to the block pattern or due to the pattern on its back. In the rare subspecies, 98% have the pattern. Did you see that in the rare subspecies? Okay, 98% have the pattern. Okay, so that's a conditional probability. If I know I've got a rare subspecies, then I know 98% will have the pattern. In the common subspecies, 5% have the pattern, but he cannot distinguish these from memory. So the rare subspecies accounts for only 0.1%, which is 0.001 of the population. Okay, so the idea is even though these of the numbers are given first, these pattern numbers, our first branch needs to be the rare versus the common. Okay, the rare subspecies versus that common subspecies. So that rare 1% of the population there, that is our first split. Okay, because I can't do 98% of the pattern because it's not 98% of all beetles have the pattern. It's 98% of the rare subspecies have the pattern. Okay, in the common subspecies, we've got 5% with that pattern. Okay, so we can figure out our complements there. And then I set up my table. Okay, so again, just like before, you're going to multiply down the branches of the table to get those probabilities. And do note that they're really small. Okay, so be careful with that when you are writing. You probably want to leave a lot of decimal places here just to be safe because the numbers are very, very small. Okay. All right, so what is the probability that a beetle has the special pattern? So it looks like about 5% of beetles have that special pattern. I can read that off of my table. Okay, what is the probability that a beetle is common and does not have the special pattern? A common and doesn't have the special pattern. So I'm looking for the overlap. That looks like that is 0.94905. I'm looking for the overlap, just the cross in the table there. If a beetle is found with the special pattern, what is the probability that it is a rare beetle? So that means if the beetle's found with the special pattern, we know that the special pattern is the given. Okay, so we want to know what's the probability it's rare. So I'm going to set that up as a conditional. Rare given pattern. Okay, that is 0.00098, which is 0.019. All right, think about this. We know that most of the rare species of beetle, 98% of the rare species have this pattern. Okay, but if you find one with the pattern, the chance of it being rare is only about a 2% chance. And the reason why is because the rare beetles are so rare that 5% of that 0.999 is overwhelming that 98% of that 0.001. So even though a large percentage of the rare beetles have the pattern, it's still such a small number that it's still really unusual. Okay, so even if he finds one with a rare pattern, the chance of that thing being one of our rare ones is still only 2%, which is very small. Okay, all right. Last question here. Don't forget about your multiple choice kind of questions. What percentage of Category 5 hurricanes occurred in September? Okay, so again, this question, when you read this, it's not what percent of hurricanes were Category 5 and occurred in September. We're not looking for that cross. It's what percent of Category 5 hurricanes. So that's the given. Okay, so up in my table, I blocked off the given, and out of those, it looks like 1 was in September. 1 out of the 3 Category 5 hurricanes, that's 33%. Okay, the next question says, approximately what percentage of September hurricanes reached Category 5? So this one's opposite. I'm not talking about all hurricanes. It's September hurricanes. So what's given is the September, what I know. So I'm only looking at that one row of 103 people, hurricanes. Okay. And of those, it looks like only 1 reached Category 5. Okay. So be careful on what direction you condition. Notice that A and B, the conditional probability, the thing that you know has changed, and that direction really does matter. Okay, the next question says, if a hurricane was classified greater than Category 3, what is the probability it occurred in June or July? All right, so we want to know what's the probability of June or July given that I know it was greater than Category 3 or that it was Category 4 or 5. So I go up here, Category 4 or 5 is everything I have boxed in yellow. Okay, and if you add those all up, 1 plus 5 plus 2 plus 9 plus 1 plus 3, okay, or in other words, 18 plus 3. Okay, in that yellow box that includes all of those, there are 21. And then out of the 21 in the yellow box, there is only 1 that is a June or a July. Okay, so that would be 21. We have 1 out of the 21, which is about 5%. Okay, so this section really just about putting things together. The biggest idea is that idea of at least 1. If you see that idea of at least 1, you want to think 1 minus none. Also, we need to continue to recognize when we can multiply probabilities because they're independent, and when we multiply probabilities because they're dependent, or multiplying down that branch of that tree. Okay. Using that conditional probability, using those tables to help us answer questions. Okay. Also, remember that even if you have a large percentage, if it's a large percent of a small number, it's still going to be a very small number.